Hello, AP Chem students, and welcome to topic 5.6, the reaction energy profile. The learning objective for today is 5.6.a, represent the activation energy and overall energy change in an elementary reaction using a reaction energy profile. So let's dive in and see what this looks like. So a reaction profile is a graph. It's the progression of a reaction relative to the required amount of potential energy, which is also called the reaction profile. So this is an image of what a reaction profile might look like, and this is the reaction that it's showing. So we're starting with carbon monoxide and nitrogen dioxide, and then we go through what is called the transition state. So once the two reactants collide in the right orientation and with enough energy, which we can determine by looking at the energy difference between the reactants and the peak of the graph. So you can see that here, and actually on this graph there is no scale, but it is labeled for you. So this is 134 kilojoules. That is your activation energy. So the reactants must collide in the correct orientation, so that C has to hit that O. And then they have to have 134 kilojoules of energy available in order for that reaction to occur. So then it reaches this point where the bonds are partially broken and partially formed. And this is called the transition state, or you also will hear it called the activated complex. This is the highest energy state for the atoms, and it's what we call, like, you can think of it as being at the top of the hill in the graph, right? So right up here. The amount of energy required to reach that phase, again, is called the activation energy. Sorry, this slide is a little bit redundant, but that's the minimum amount of energy that's required for the reaction to occur. So if the reactants collide in the correct orientation, but they do not have enough energy, they will not be able to make it up and over this hill. You can kind of think of it as being like a roller coaster. If it doesn't have enough energy to pull up the hill, then it would just slide back down again and it would not ever go. Kind of the same situation. So then let's talk about the energy. So the energy required can come from the kinetic energy of the molecules if they're moving faster, or it can come from the heat energy of the surroundings, but not all molecules will have enough energy to react. And we looked at that already when we talked about Maxwell-Boltzmann graphs. That proportion of molecules that will have enough energy to react is dependent on temperature, in part because they can use that to increase the kinetic energy of the molecules. The Arrhenius equation allows us to graphically determine the activation energy of a system using the rate constant and the temperature values. You will not have to do any calculations with the Arrhenius equation, nor do you need to know the equation itself. But you do need to know that if you graph 1 over temperature versus the natural log of the rate constant K, then the slope of that graph is equal to negative E sub A over R, okay? Now, this would be the R that uses joules, okay? So that's the 8.314 value. So we have seen this come up on the test before, mainly just by asking kind of how could you determine the activation energy, and you would use the slope from this graph, 1 over T versus natural log of K. And that's pretty much it for this topic. So what should you be able to do with this? Label the areas on the reaction profile, the reactants, the transition state, the products, and the activation energy. You should qualitatively apply the relationship between temperature and activation energy, demonstrating the Arrhenius equation to demonstrate the impact of the change in temperature on the rate of an elementary reaction. So if we go back here, then you can see that relationship, right? As temperature increases, then you can see what's going on here. Okay, so that is all that I have for this topic, and I will see you again soon for the next one.